So carrying on with these these shear force diagrams and calculating moments and plotting now what we call the bending moment diagram. This introduction here introduces, it's something that will probably make a little bit more sense when we've done some work on calculus. Those of you who've done it fairly recently will recognize this as a differential. And we know that the shear force is given by the rate of change of the moment to the distance you are away from the pivot. The rate of change of moment with radius, which is the differential. And so it turns out that the gradient, the shear force is the gradient of a bending moment diagram. So if I want to know what the gradient of a bending moment diagram at any point is, it's the shear force. And equally, this symbol represents what's called the integral, which is the other calculus thing that we're going to talk about. That gives us the area under a stress curve, which gives us a value of the moment at any point. So what we need to take from this before we look at the maths later on is that if I want to know for a bending moment diagram, in other words, what's the moment acting on this beam at any moment? When is the moment the greatest? What is the value of that moment due to all these forces at various points along the beam? What are those values? I can draw it on a bending moment diagram. How do I get these values? To get the bending moment, I look at the shear force. I look at the gradient rather of the shear force diagram. That will give me the value of the bending moment. And if I want to know what the moment is at any point, I'll find the area underneath the stress curve. So the shear force is given by the gradient of a bending moment diagram, and the value of the moment is given by the area under the curve. So if we draw a shear force diagram, we can use that to work out what the bending moment diagram is. We need to find the area underneath the curve at various points. We've just done one. So for this one, here, when I started to plot these out, we're going to want to find out what the area is underneath here, because that gives us the moment. And if I want to know what the shear force is at any point, that will be the gradient of the bending moment diagram when we get to it. And you can see that's a rectangle. That bit looks a bit like a rectangle. That's a triangle. If I extend this down here, here's another triangle, and so on. So we can find these areas just by using the relevant formulae, and that will give us the bending moment. So let's apply it and see what happens. Here's an example, the first one you've got in your book. The first thing we need to do is find out what the reaction forces are at A and B. So I'll just pause this while you very quickly do the moments, more practice on that, and then we'll put those values onto this diagram. Okay, so we've got these values. It's just using method 1 or method 2 to get the reaction forces at A and B. So we can put them on here. B is 8.8. A is 9.16. So the reaction force at B was 8.8 and 9.16. So now we can draw our shear force diagram here. And note underneath I've left room for this other diagram called the bending moment diagram. So we start off at 0. This is our 0. And it's shear force up here. This is the shear force. Measured in this case in kilonewtons. So we specify the unit at that point. We're working in kilonewtons. So we're going to go up 9.16. So you've got in mind a scale, 5, 10, 15, 20, something like that. So 9.16, it doesn't have to be exact, it's only giving us an idea where these forces are. Just so long as they're in roughly the right place on here, that's okay. So we're going up to 9.16. And then nothing else happens until we get to the 8 kilonewton mark. So we go across to 9 to there, and then come down to 1.16. So you can sort of put on there what the values are, and then we can carry on across and draw the shear force diagram in. Then we come down another 6. So what's that? 1.16 minus 6? 4.84, is it? Have I done my arithmetic correctly there? It needs to be, so check me out there. 1.16 minus 6. And then nothing happens until we get to the 4 kilonewton mark. And then we go down another 4, which takes us to minus 8.84. Across, and then the reaction force up takes us back to 0 again. 8.8, but that's a rounding issue, isn't it? So now we have the bending moment diagram. This is the bending moment diagram down here. This is where it starts. That's a 0 here. There. Moments start at 0 and end at 0. So your diagram should start and finish at 0. Because it's supported at those ends, so the moment at that point is going to be 0. Remember what we said at the beginning, that the value of the moment when we get to here, what's the moment when we get to this point here on the diagram? That moment is the area underneath here. So we've got to work out the area underneath that rectangle. That will give us the moment at this point here. So the area underneath that diagram is going to equal, and we can draw it on the diagram, we can write the area equals 9.16 times the distance, which is 3. 9.16 times 3. Yeah. Yes, down to the line, yeah. No, yeah, no, down to the line, the whole area. And 27, whatever that is, comes out to be 27.48. If we think about the units of this area, the units are given by the units along this axis times by the units along this axis. Kilonewtons for the shear force up the y-axis, and distance along here. So the unit is in kilonewton meters, which is the unit of the moments. So that confirms that in a way that we're finding the area here is giving us the moment. Now what that means is that by the time we get to this point on the axis, on the beam, we've got to a moment of 27.48. So we just draw a point here, and that will be at 27.48, because that's the moment at that point. And then we think about, well, how do we get there? Is it a curve? Is it a straight line? So what is it? The gradient of the moment diagram, which is this, the gradient of this bending moment diagram, is given by the value of the shear force, is what we said at the beginning. But what's the value of the shear force? 9.16. So what that means is the moment is increasing at the rate of 9.16 per metre. And if you think about it, 3 lots of 9.16 gave us our 27.48. So we're going up at that rate, and we get to that moment by the time we get to there. So it's a straight line with a gradient of 9.16 between there and there. And that's how the moment is increasing as we're moving along the beam. 0 at the start, and increasing at the rate of 9.16 per metre until we get to here, at which point it's 27.48. What do we do now to find out what the moment is here? By the time we get to this point on the axis, what's the moment? How do we find the moment? Same procedure. Right. Find the area under here. So if you find that area underneath there, it's 1.16 high by, from 3 to 7 is 4. Will give you the area underneath here. So here the area equals 1.16 times 4. So 4.64 is the area underneath here. But this area is above, it's positive, it's above the 0 on this line. So effectively that's adding to the moment here. The moment is going to continue to grow until we get to 4.64. So in other words, we add 4.64 to this value, and that will give us a moment at this point. So we can work that out. What's 27.48 plus 4.64? And that will be this point here. (32.12) is the value. How is the moment changing between here and here? The gradient between here and here is given by the shear force, which is 1.16. So in other words, it's going up at the rate of 1.16 per metre between here and here. So that by the time we get to here, it's 4 lots of 1.16, i.e. the area underneath here. So that's how why that works. And so we can draw another straight line in between there, and that will be how the moment's changing. So at any point along this beam, we can say, what's the moment on the beam at this point? It's that value, whatever it is. Now, this area is below the 0, so now the moment is reducing, it's negative. So we're going to start coming down now. Another way we can tell that is, remember the gradient of the bending moment diagram is given by the value of the shear force, which is now negative, and a negative gradient looks like that. So we're going to start reducing the moment now. How much does it reduce by? The area underneath here. And then we work out the next bit, which is from here and here, this bit, and we should end up back at 0 by the time we finish. So I'll just let you finish that off. So we have the area of 14.52, which takes us down to there, and that area takes us down to here. Note that the gradient here is given by that value. So this is steeper. The gradient is going down at the rate of minus 8.84. So that's this gradient, but this gradient is minus 4.84. So steeper gradient here, and you can see that from the value of the shear force at those points. The value of the shear force at a point gives you the gradient at that point. So the gradient here is constant, 8.84. Therefore, the gradient is constant, it's a straight line. Notice other things about this diagram worth pointing out. That this is the value of the maximum bending moment. So I can work out where the maximum stress is on this beam, the maximum moment trying to bend this beam. Notice also that that coincides with where it cuts the zero on the shear force diagram. So this, without working out, it doesn't tell you what the value of the moment is, but the shear force diagram tells you where the position of maximum bending moment is. So this is the position of maximum bending moment. If I want to know what the value of that bending moment is at that point, I'm going to need to draw a bending moment diagram. But at least it tells me where it is.